So now we'll turn our attention towards specific simple harmonic oscillators, and without a doubt the most important one, the one that you would be most likely to encounter in a problem, particularly on a test, would be the horizontally oscillating mass on a spring. And we're going to, while I'm explaining this diagram, you should be drawing this to the best of your ability. This shows a spring oscillating through one full cycle. So if you can imagine the horizontal spring connected, and we pulled the spring out to its maximum displacement, which you should know is called the amplitude, and then released it, what would happen is the spring would provide a restoring force that pulls the mass back towards the equilibrium position. When it arrives at the equilibrium position, it will overshoot that position and then cause the spring to become compressed, leading us to the third position, where the spring is as fully compressed as it's going to be at the other extreme displacement, at the other maximum displacement. And then at that point, the spring will begin to push back on the mass, causing the mass to shoot back towards equilibrium, but overshooting the equilibrium position until it finally returns back to that initial position where we released it. And then from that point, this will continue to move back and forth through that same cycle over and over again. The spring obviously could be oriented in a vertical position, something like this, but for the most part we probably won't look at that situation too much, and I'll show you the reason why that is. Let's draw a Freebody diagram. I'm going to use this space right here to draw the Freebody diagram for this position up here at the top. At that position at the top, there is of course the force of gravity, mg. And this spring is not just floating in space. It could be on a number of things. The mass could be on wheels, which would provide very little friction. It could be on an air table, which would provide very little friction. It could be on oil or ice. There's any number of things that we could put this horizontally oscillating mass on so that it experiences very little friction. And the upward force that it experiences then would be generally due to some type of normal force, whether it be air or oil or ice or it's on wheels, whatever it is. There is some upward force that is balancing the force of gravity. And for this position, number one, we would be looking at a force pointing towards the equilibrium position, and that would be the force of the spring. So the reason why we're going to focus on this version, this variation of the problem, is because the only force that we have to deal with in the direction of the oscillations, which in this case is horizontal, is the force of the spring. We don't have to deal with any combination of normal force or gravitational force and the spring force. It's just simply the spring force, and that is going to make the problem just a little bit simpler. Let me remind you from previous chapter that the force on a spring was discovered by a gentleman named Hooke, who created something called Hooke's law, and that is that the force that a spring experiences is, first of all, opposite to the direction that you displace it. So that is to say that if you pull the spring outward, the force will be to the left. If you push the spring to the left, the force will then be to the right. That's where the negative sign comes from. The force depends on the amount that you've displaced the spring, and graphically speaking, that looks something like this. So if we make a graph of F versus X, the displacement, you would find that initially the force is very small, but it grows very rapidly. The more that you displace it, the greater the amount of the force. And clearly you can see that if I were to solve for this property, this constant of the spring called the spring constant, that would be the force divided by x, so the slope of this is equal to the spring constant. And that's frequently a way that you would be asked to solve a problem, is that they would give you a variation of a graph of force versus displacement, and using that force displacement graph you could pick any point on that graph to determine the spring constant, because of course this does go through the origin. So Hooke's law is that the force acting on a spring is F equals minus kx, but remember that the second law says that the force acting on any object is its mass times its acceleration. So you can see these two forces are the same force, and we can combine them together to say that MA is equal to minus KX. And you can hopefully see that we're just one step away from having an equation for simple harmonic motion. Remember, the equation for simple harmonic motion is that the acceleration is directly proportional to, but opposite to, the direction of the displacement. K in this case is a constant because it's a property of the spring, and as long as we don't change the spring, that K property will not change. And of course the same thing would go for the mass. As long as we don't change the mass, then that is the property that's not going to change. Effectively, these two properties, K and M, these are constants of that problem. So if we make the last final step, we get A is equal to minus K over MX. And of course that is the version, that is the form of the simple harmonic motion equation, I should say. And this is where I was saying before that the omega squared value is going to be something that you can derive based on the specific forces that are acting on that particular simple harmonic oscillator. So in the case of the spring, it turns out that omega squared is equal to K over M, or omega is equal to the square root of K over M. So this is something that you shouldn't have to memorize, because if you think about how simple it was to derive this, the force on a spring is minus Kx. The second law says that force is ma. You set the two equal to each other. You can solve for A. You bring everything that's not A and X together, because these are all constants for that particular object, and you end up with an equation for simple harmonic motion. And then using the omega squared value, you can see that omega squared must be equal to this thing that's in front of the x. And that gives you a specific form of the equation for the horizontal spring in this case. Omega is square root of K over M. Of course, remember that T is equal to 2 pi over omega, and so that means that in this case T will be equal to 2 pi times, now realize if omega is on the bottom and omega is the square root of K over M, then that means that when we invert that and bring it up to the top, we'll end up with an equation for the period of motion that is 2 pi square root of M over K. Okay? So that is the spring. Now you may be given the K constant, you may be asked to solve the K constant using a graph, you may be given the period of the motion or the angular velocity and be asked to solve for K. Obviously you can see K is involved in both of these two things. It would be very unlikely that you would be asked to solve for the mass. That would be kind of an unusual situation. So let's apply this to a pretty straightforward, simple problem. So what I would suggest that you would do is that I'll stop for just a moment and give you a chance to pause the video and copy the problem down, and that way we can talk about it and you don't have to be writing while you're thinking about what I'm talking about. Okay, so the way that this problem is set up is that I'm going to draw a force displacement graph, and I'm going to put numbers on it, which I didn't put on the previous graph. And as soon as I put numbers on that, we can then use that graph to determine things like the spring constant, for example, the angular frequency, the period, and then the regular frequency, which this is the one that would be measured in hertz. And in this case, what we're going to do is to attach a 2.5 kilogram mass to a spring, which is represented by this graph. So we're going to take x in centimeters and force in newtons. Here's our graph. And we're going to pick any arbitrary point, and I'm going to put values. And in this case, let's assume that for this particular point, the spring was displaced by 0.75 centimeters. Oh, sorry, 75 centimeters. Let's just make it 75 centimeters. And in the case of the force required to extend the spring by 75 centimeters was, we'll say, 32.0. Okay, so this spring, when extended by 75 centimeters, requires a force of 32 newtons to cause that kind of stretch, or that elongation. So the first thing that we're asked for is the spring constant, and F is equal to minus kx. We're not going to worry about the minus. This is just the direction of the force, but K would be equal to F over x. Now, the reason why, even though this is the formula for the slope, we don't have to worry about delta F and delta x is because the spring constant graph is always going to go through the origin. So one of the values you could always imagine as being 0, 0. So any point along this graph is going to allow you to calculate the spring constant, which in this case is 32.0 divided by, now realize that the spring constant must be, or the displacement I should say, must be in meters. So we're going to turn that into meters, 0.750, to give us a K value of 42.7, and that would be newtons per meter. So important that you make sure that you keep the units in newtons per meter, not newtons per centimeter, because that's going to cause some difficulty with some of the later properties that we're going to calculate. So after the spring constant, once we know the value of K, we can then use that to calculate the angular frequency, because in this case omega is equal to the square root of K over M. That's 42.7 divided by the mass, which we were told was 2.5 kilograms. And so in this case, we get 4.1. If you think real quickly what the units are for the angular frequency, this one is in units of inverse seconds. Okay, not hertz, just inverse seconds. Remember, really the angular frequency is radians per second, the number of radians per second that we're moving through. So we've got the spring constant, the angular frequency, next would be the period. Remember that the period is 2 pi over omega. So in this case, 2 pi divided by 4.1. That gives us a period of 1.5 seconds. And finally, the last thing is to calculate the frequency. Remember, frequency is a very simple formula. It's simply the inverse of the period. So for our example, that's 1 divided by 1.5, or a frequency of 0.67. And remember, this also has units of inverse seconds, but these inverse seconds are referred to as hertz. So this gives you an idea of some of the things that you can do with really very minimal information. Just a simple graph of the force versus displacement and the mass of this object, and I can work out many of the properties of this simple harmonic oscillators. Before we leave this particular simple harmonic oscillator, one thing that I want to make very clear that it might not be obvious to everybody is, if we look back at the formula for the period, you'll notice that one property that is, I think, maybe glaringly absent, and that is that the period of its motion does not depend on how far you stretch it. So, not to say that the simple harmonic motion equation doesn't involve the displacement, but the formula for the period and the angular frequency does not depend on x, how far you displace it. That is to say that whether I displace this by a small amount, a medium amount, or a very large amount, I am going to get the same period regardless. Okay, now the acceleration that's experienced will be greater or smaller depending on this displacement. There are properties that do change. Of course, the amplitude would change as I pull it farther or less, but the period of its motion will not depend on how far you displace it. And I think that that's something that's not particularly obvious when you think about mass oscillating on a spring. Most people probably assume that the greater that you displace it, the longer that it takes for it to go through its period, but it actually doesn't depend on that at all. It simply depends on how much mass you put on the spring and the spring constant, how strong that spring is.